so it looks like we can start. Hi everyone, my name is Palina. I am a verification engineer at Runtime Verification, where I work on developing the tool Kontrol that I'm going to introduce today. Runtime Verification is a technology startup providing security services to blockchain as well as some other industries. And in blockchain, not only we do traditional security reviews or audits, but we are also experts in developing and using formal verification tools. And in this talk, I would also try to explain why that matters for security. By definition, security is the state of being free from danger or threat. And as you probably know, at least in blockchain, that's pretty much impossible, even though we should try to get as close to that as we can. If we look at the DeFi protocol and the process of executing its transactions, we would see that there are actually a lot of components in this technological stack, and unfortunately, the issue might sneak into any of them. So in the case of a DeFi protocol, there might be issues in the Solidity code of the protocol itself. There can be compiler bugs, front-end vulnerabilities, as well as some other potential issues in the lower level layers in this stack. And also, unfortunately, in security, so there is no security in isolation, right? Even if Solidity code is correct, it can still be exposed by bugs in compiler or in CPU, a Cosmic Ray, flipping some bits in some computer's RAM, and so on and so forth. But the good news is that there are some tools that actually help us make sure that all parts of this stack are secure, and Kontrol, the tool I'm going to talk about today, is working on the Solidity and EVM smart contract level. So on this slide, I have put some of the existing techniques that can be used for security and correctness assurance of smart contracts based on the level of confidence that they provide us in terms of the security of the implementation we are looking at. And I do know that saying that manual review provides us with this lowest confidence in the results is debatable. But what I want to say is that generally we have no guarantees in terms of how much the particular auditor, how much time he's going to invest, how much effort this person is going to invest in this review, how confident he is in this particular with this particular implementation. So it is very dependent. The quality is very dependent on the particular individual. At the same time, static analysis provides us with a bit more consistent results in that matter. These tools usually operate on the high-level source code or some intermediate representation, and they typically perform pattern matching to identify some vulnerabilities, some common types of vulnerabilities that exist in smart contracts. Slither is a prominent example of that, and they are actually very useful with searching for these common vulnerabilities in smart contracts. However, unit testing, fuzzing, and ultimately formal verification provide us with more and more confidence in the correctness and security of the implementation we are analyzing. And now I'm going to explain why exactly. So that is, let's consider this example that I have prepared for this talk. Let's assume that your project uses this library to perform some arithmetics. And generally, in Solidity development, there are several libraries implementing fixed point arithmetics. So that is just one of them. And assume that your project, your project uses this library, and this library releases a new version. And this version, among others, contains this change. So even if you are looking at diffs in your dependencies, which I think you should do, you might still, I guess there is a chance to not notice this particular change. So what this function does is multiplication. So it just multiplies x and y. And normally, it only reverts if there is an overflow that occurs in this multiplication. But I have also added another condition why it would revert. So I'm forcing it to revert if x is also equal to this very specific, very particular hard-coded value. And I just tried to disguise it very lightly, so it looks like a bit mask, and it looks less suspicious, but generally, for the purposes of this talk, I didn't try to hide it very well. So that implementation is actually based on Solidity. That is a library, and there is a link to it on the slide. We actually proved it correct, so this particular function is safe to use if you're not using this modified version. So let's talk about why analyzing that is challenging. And this function, that is a gas-optimized implementation. That is why it's implemented right in assembly. And together with gas optimizations, it also provides some challenges for reasoning about its security. And one of the problems is that because it's an assembly, static analysis tools provide limited support for it because they usually operate on this high level of the source code itself and some high-level intermediate representations. In addition to that, for some of the vulnerabilities, we actually do have compiler checks that are just inserted automatically, and starting from version 0.8, Solidity, for example, inserts this automated checks for overflows. However, in this case, if the smart contract is written in assembly, you won't really get any of these built-in compiler checks. At the same time, in this particular case, we have just added this custom condition for this function to revert. So it's a not standard problem. There is no pattern that would detect it. So none of these techniques would really help in this case. And you actually have a better chance of fighting this just by doing the manual review. But assembly is less readable than source code. So this bad readability also provides additional challenges when it comes to the security of this particular function. So what we can do in order to try to reason about this function's correctness, we can write some unit tests. And here on the slide, I have examples of some of these simple unit tests. What they do, they call this small what function that multiplies two values with some concrete values. So here we have this test small what, and what it checks is that multiplying 5 by 0.5 returns 2.5, and that works. So that provides us a little bit of confidence in the fact that this function actually works correctly because, well, at least it can correctly multiply these two values. Unit testing generally is very useful, very usable. It could 100% be part of any development process. However, the problem is that it provides us with this very limited information about all these possible behaviors that this function can have. We don't really know how it would work on some other values other than these concrete ones that we have tested before. You can increase coverage by just adding more tests, but it would still be hard. It would take a very long time to enumerate all possible values. And you can also, it is recommended to increase coverage by adding more tests that explore different execution paths. So if you have a revert condition, you can, or an if statement, you would like to write some tests that expose both of these branches. However, the problem is that some branches may not be obvious. So in addition to these branches that we see in the source code, or these conditional statements, compiler automatically inserts some of the checks itself. So for example, because this function, all the functions here are not marked as payable, which means they can't accept Ether. So if this contract received Ether, if any of these functions do, then it's going to revert, and that is the compiler introduced check. So there are more branches than you think most of the time. And the summary here is that unit tests are very useful, can expose some logical flaws, but they only explore a single execution path in a smart contract. So what we can do to increase coverage further, we can do fuzzing. So we can write a more informative test, and we can fuzz it. So here on the slide, that is a Foundry test. So Foundry is the development framework, a very popular one. It's written in Rust. So what it lets us do is to write this more interesting parametric test. As you can see, different from this unit test we were looking at, it now accepts two parameters, x and y. And what we do in the body of this test, we are just checking that if x multiplied by y doesn't overflow, then the result we are getting from mul-what for multiplying these two values is the same as we would get if we just multiplied them in Solidity. So that is the readable implementation that we can actually inspect ourselves and make sure that it's correct. Alternatively, if it does overflow, then it should revert. So that's what we are trying to see here. This test is going to fail because there is also this specific revert condition that we introduced ourselves. And this test can be fuzzed. So the general idea behind fuzzing is, I think, very well explained by this tweet you can see on the slide, with a joke saying that the QA engineer walks into a bar and orders 1 beer, 0 beers, a lot of beers, -1 beer. So that is what fuzzing does automatically. It just keeps executing this function with random values, hoping to find certain edge cases. And generally, fuzzing also is very useful. It can help uncover some edge cases and some problems. However, that it doesn't find the issue in this particular case. And so it cannot find this revert that occurs if x has this super specific value, because it just is too specific for it to get randomly generated in this limited number of runs. And that is the summary of the fuzzing part. So fuzzing examines a lot of different execution paths. It can uncover a lot of branches and explore the corresponding execution path. However, there is no guarantee that it will examine all of them. And here is how Kontrol can help. So different from these other tools that we have considered that perform concrete execution, Kontrol uses formal verification, which means that instead of running this code concretely, we're actually going to mathematically prove that the implementation in Solidity and the gas-optimized one, are behaving exactly the same way. We have this foundry integration in Kontrol, so we are going to actually analyze the same test. So this test mul what function and the one in the previous slide are exactly the same. And we'll just run Kontrol on top of this test, and we will see that even though the test is the same, the results are actually different. So Kontrol is going to tell us that the proof had failed, and it had failed if it fails if x has this specific long value, which actually corresponds to this 0xff that I have used in the original implementation. That's just the decimal value for it. So to summarize, because Kontrol is different from this concrete, from the tools that perform concrete execution, since it is powered by this the act of mathematical proving, Kontrol can explore all execution paths and uncover all these possible edge cases. And due to its integration with Foundry, if your project has Foundry tests, you can just give Kontrol a try and try to run it on the existing tests, which means that there is little to no need for some additional specification. Kontrol is open source and it's a command line tool, so we actually do recommend running it on CI. We have this GitHub action that you can find the link to on the slide, so you can actually add it and introduce it to our CI, so the tests can be run either periodically or they can be re-triggered by any code change, and that would help ensure that no code changes or no changes in the dependencies introduce any issues that could have been caught by formal verification. And in addition to that, the example I have used in this talk is actually quite simple because I wanted it to fit into 15 minutes. But Kontrol can cover a larger set of properties, including security properties, correctness, conformance to the standard. We use it ourselves internally. We use it in the engagements with our clients. So you can actually try to run it. You can run it on the larger code base and verify some more interesting properties, in addition to this equivalence check-in that we have done today between the Solidity implementation for a specific function and a highly gas-optimized one. So that it can also provide you with some guarantees in terms of how exactly your gas-optimized and not very readable code behaves. In addition to that, we also plan to generate ZK proof objects for this proofs that we generate using Kontrol, which means that these proof objects would certify that the code that has been verified and the code you're analyzing, the code you are running, and the code that has been analyzed is the same. And these proof objects could also include some verification artifacts that we produce during this mathematical proving. We actually are raising at the moment, so if that is something you're interested in investing, please let us know. And finally, one other thing I would like to mention is that in addition to Kontrol, we actually have more tools that we developed at runtime verification. So please feel free to explore them. And one of these tools is Symbolic. Symbolic is a debugger for Solidity. And similar to Kontrol, the actual verification happens at the bytecode level. So even though the input is this Solidity contracts and Solidity tests, we actually, as you have seen, we have no problem analyzing inline assembly, and also the code the code that is being verified is also the same code that would be deployed on chain, and you're going to execute there. So Symbolic is as I've said, it's a Solidity level debugger, but since it is powered by Kontrol and formal verification, you can explore all possible execution paths, and you also have access to this very detailed EVM level information about the execution stack and generally just the state of the program, the state of the contract that you are looking at. So it has this VS Code interface, so it's very usable, and it hasn't been released yet, but there is a demo that we have published. You can find it via this link that you see on the slide. And in addition to that, we are currently looking for beta testers. So if that is something you would be interested in, please let us know and please sign up. That is all that I had for today. These are some of the socials using which you can stay in touch with us and follow our updates. Please feel free to join our Discord and share your feedback or report any issues you might have encountered when using our tools. And these are also the link to Kontrol documentation and GitHub. As I've said, it is open source and it works with seamlessly works with Foundry projects, so that is something you would be interested in. Please give it a try or let us know. And yeah, I guess that is all for me today. Thank you very much.